Hey guys, welcome back to CMTEQ channel. This is tutorial 9 on short circuit MVA calculation. Now imagine you are an electrical engineer, a power system technician, and you have been asked to find a sub-transient fault current, okay, for a three-phase symmetrical fault at bus 1, right? So this is bus 1 right here, and you need to find the fault which is basically located at the secondary of this transformer T1, okay, and you are required to use 1000 MVA and 20 kilovolt as base in the zone of generator 3. So that basically means generator 3 here have a base voltage of 20 kilovolt, and that is the base that you're going to use to solve your entire network, right? So what you have to do here obviously is to get your network variables, and based on your network variable you can establish your per unit diagram, your per unit impedance diagram, and from there you can start solving until you're going to get to this fault here, the three-phase symmetrical fault that is located on bus bar 1. Now our network equipment have the following ratings: generator 1, a 500 MVA rated and 13.8 kilovolt; generator 2, 750 MVA, 13.8 kilovolt with a per unit, all per unit of 0.18 J per unit; generator 3 with a 1000 MVA and 20 kilovolt rating with an all per unit of 0.17 J per unit. Now generator 3 ratings are the one that we are said that we need to use as the base for our entire network. Now transformer T1, a 500 MVA, which is a delta star coupling transformer; transformer 2, also a 750 MVA, okay, also a delta star; and transformer 3, a 1000 MVA. Now as you can see here that the rating of each one of these transformer correspond to the rating of the generators as well. So you have this transformer 3 that is rated at 1000 MVA, okay, but generator 3 here also is rated at 1000 MVA, so it need to be proportional. So you cannot put a transformer that is rated at 500 MVA to transform or handle the power of 1000 MVA that this generator is capable of supplying, right? And one other factor that we can see here is that all the transformers, they are step-up transformers. As you can see, they are stepping up the first one 13.8 to 500, 18 to 500, and 20 to 500 kilovolt. So you can see generators are usually going to supply on a low voltage, and it needs to be scaled up, step up for long distance transmission, and then later on it must be stepped down for low voltage distribution, okay? And we can see that also our circuit, the line voltage here is 500 kilovolt, and each line impedance is rated at 50 ohm. So this basically means the zones here from 1 to 2 to 3, it could be kilometers and kilometers of transmission line, and it is said that it's just rated at 50 ohm, right? That is the line impedance, and this line impedance will actually help us to calculate what we call as ZA, right? ZA, which is the Z actual of the line, okay? So it is 50 ohm for all these bus bars. Now, right, we are now moving on, and before we continue, please guys, don't forget to subscribe to CMTEQ channel. If you like this tutorial, please, I will appreciate a thumbs up, just a thumbs up, like the video, and drop a comment if you have any question. All right, so now we know that we need to convert this entire circuit into a per unit diagram, right? The per unit impedance diagram that will actually help us to get to the bottom of this fault here. We need to follow the money. So by that I mean we need to follow the path with least impedance, right? Because that is now the path in which the current is going to take. So as you can see here, this is a fault, right, to ground. So it's a line to ground fault. So which means all the current, they need to rush to ground because that's the path where there is least impedance. Anywhere else there's going to be some kind of impedance that the current need to go through, but once the current get to ground, is happy because it's shorted. All right, so we need to build that impedance diagram that going to take us to where the fault current is. That way we're going to find that three-phase symmetrical fault, okay, at bus 1. Right now, this here is the general formula for per unit system. So it's a Z per unit new that we need to find, but doing so, we're going to need to use the Z per unit old. So these are these variables, right? The Z per unit old that were provided for the generators and the transformers. Since we are now going to calculate the Z per unit new, we're going to use Z per unit old. And then SBN is the base apparent power new. So this basically means the 1000 MVA we're going to use. And then old is going to be the base apparent for the generator. For instance, here is going to be the 500 and new is going to be the 1000. And equally so on the voltage, VBO will be VB old. That's going to be the 13.8 kilovolt that the generator is supplying, odd on the primary of the transformer. And VB new is going to be the one the generator is supplying. And this quotient here, we can see that since the generator supply here to the transformer is equal to the transformer primary voltage, so that basically is going to cancel this equation here. So having said that, we can then deduce that generator 1 have a Z per unit new of 0.4 J per unit, and Z per unit new of the transformer is 0.24 J per unit. Generator 2 is 0.24 J per unit, and T2 is 0.133. So if you replace all the parameters of transformer 2 here, the 750, right, and the 0.1 J per unit into this formula, you're going to find surely this value here. And generator 3 is that, and transformer 3 is 0.1 J per unit. And as stated here, X1 is equal to 50 ohms. So basically the Z actual of all these three zones, they are actually 50 J per unit for ZA1, ZA2, and ZA3 for each one of these bus bars. Now, because we know what is Z actual, right, the actual impedance of the line, we can then calculate the base impedance of the line, right? That is actually based on the voltage of the zone. Now, we know that all these zones here, they basically stepping up. They are based on step-up transformers that are all stepping up to what? To 500 kilovolt, right? As stated here. So that basically means this entire zone here, right? We can call it zone 2. This entire zone have the same base voltage, right? So ZB or Z zone here. So V base, all right, or V base of the zone is actually 500 kilovolt. So if we know what V base of the zone is, we can then deduce from that, say that Z per unit of the line, right? Z per unit of the line is equal to Z actual divided by ZB. Okay, then we can calculate what is ZB. Now, in order for us to calculate Z per unit of the line, we only need ZB, since we already have Z actual of the line, which is equal to 50 ohm for each one of these lines from different transformers. So now ZB, that is a simple situation also, because VB here is 500 kilovolt for all transmission line. So we can deduce that ZB is equal to VB zone, right, divided by SB. But the VB zone here is 500 kilovolt for all the zones, okay? And SB new is the 1000 base MVA that we needed to use there. So replacing that into the formula, we got a ZB, all right, of 250 ohms. So that is the base impedance of this network here, of this zone here. Now we can use that to then calculate our Z per unit of the line. So the Z per unit of all those three lines, since they are all equal to 50 ohm, right, as given here, right? So we can then say Z per unit of line 1, line 2 is equal to Z per unit for line 3, and that basically Z actual divided by ZB. So that's a 50 divided by 250, and that gives us a 0.2 J per unit, right? So this makes the task very simple. So we know that all these sections here, they've got the same Z per unit of the line impedance of 0.2 J per unit. Now we can go ahead and draw our impedance diagram. Now this is quite a bucket impedance diagram, but we can see that G1 here is 0.4 per unit. Okay, so there is G1, and we can see that T1 is also 0.24 J per unit, right? And then we move on. Line 1 here, line 1, Z per unit for line 1 is 0.2 J per unit as we've calculated there, and for line 2 will be the same, and for line 3 will also going to be the same, right? Then T3, the per unit of T3, we know that it's 0.1 J per unit, and G3 it is 0.17. Then we move on T2 here, that's what we got, 0.133, and G2 is 0.24 J per unit. So this basically sums up here our per unit diagram. Now we can continue moving on. We can further reduce this impedance diagram so that we need to get to the bottom of this fault here. Remember, this is where our three-phase symmetrical fault is located, on bus 1. So we need to reduce this network here so that we can follow the path in which the current will be taking when this fault occurs. And reducing our diagram further, we're going to get the following diagram. So here we can clearly see that the 0.64 per unit here is a combination of both G1 and T1 per unit. Then we've got 0.2 per unit of line 1 that is still there, and the per unit on T3, G3 and line 2 combined give us a 0.47 J per unit, and the per unit system or the per unit impedance on generator 2 side and transformer 2 side give us a combination of 0.573 J per unit. Now here we can see that generator 2 and generator 3 are actually in parallel because they are joining to this particular point, and they will be in series with the impedance or the per unit impedance of line 2 or line 1, and they will be in series with the per unit impedance of line 1, which is 0.2 J per unit. So basically we need to get the parallel combination of this and add it to that. So the parallel combination of those two per unit values will be 0.47 times 0.573 over 0.47 plus 0.73, and that gives us a 0.258 J per unit. So that is now the combination of these two generators in parallel, right? So then we need to take this value here and then add it to the 0.2 J per unit, and that gives us a value of 0.458 J per unit, right? So this should be J per unit, right? So then from here we can then go ahead and say that the combination of T1 and G1, as we've gotten here, must then be in parallel with this whole expression that we just combined here, because the fault is now going to be at this point here, point F, right? So having said that, we can then move on, and this is a situation. So the situation is now 0.64 J per unit is in parallel with 0.458 J per unit, and that gives us a parallel combination. So basically 0.64 times 0.58, okay, 0.458 over 0.64 plus 0.458, and that is indeed 0.267 J per unit. So this is now the total per unit impedance as seen from this point where the fault is located, and that is the total per unit, the total impedance that the current will see when it tries to follow the money to come to this point here, right? So from there we can then calculate the I per unit, which is 1 over Z per unit total. So that is 1 over 0.267, and that basically gives us a per unit current of 3.74 amps. Now if you know the per unit current, you basically can find the short circuit current, because we know that I short circuit is basically I line times I per unit. So we first need to calculate what the I line. So what is the I line? I line is basically given the same formula that we are able to calculate the SB new. So then we can make I line the subject of that formula. So this gives us a value of I line that is 1154.7 amps, and that is 1000 MVA divided by 500 kilovolt times the square root of 3. Now remember, this 500 kilovolt is the voltage on the line here. So this line here, or the zone here, this zone here, have a VB of 500 kilovolt. And why is it 500 kilovolt? Because this transformer T3 and T1 and T2, they are all stepping up. They're stepping up to a voltage of 500 kilovolt. So this whole line is energized or at a potential of 500 kilovolts. So that's the one we use here to get the line current. Now that we've got a line current, indeed I short circuit is I per unit times I line. So all we have to do is to replace into the formula, so we know what is our I per unit. We now have found our I line. We can then deduce that the I short circuit, right, the symmetrical fault on this point here on bus 1 is 4.325 kilo amps. That's the short circuit. Now if you want to try something and just to practice yourself, try moving this fault here from point 1, bus 1 here, and place the fault anywhere. You can place the fault here at this point here, right? So you can name this F2, or you can place the fault anywhere else. Let's say you place a fault here, right here, okay? And then you can name these also F3. Now all of these are going to give you different value of the current, because wherever you place your fault, you can place your fault also here. You're going to have a different value of impedance, as these ones supply the current. They all try to follow through where the fault is. So already the impedance value changes, and that dictates to you what will be the per unit value and what will be the short circuit current to that point. So guys, this is it for this tutorial, and this is exactly how you set up and get your short circuit current calculation. And based on the level of the fault you find at this point, you will understand, you will know what kind of protection you need here, so that it can break this fault without causing any fire or system interruption or a major outage. Thank you guys for watching. I hope you found this tutorial helpful, and please give this tutorial a thumbs up and subscribe to CMTEQ channel. Until next time, stay tuned for more tutorial of this nature. Cheers.